This is video number 9 concerning the design of concrete slabs. We will handle in this video the behavior of two-way slabs. We will first start with the general thin plate theory or thin slab theory. You have 6 different types of isolated slabs. That is a ground view of a slab. This is type 1 slab. It means that the type 1 slab is rectangular and it is simply supported on all sides. So if you make a cross section here, then this is the slab. This is the uniform distributed load Q in direction of A and simply supported on both sides. You make a cross section there and then you have this figure. So type 1 is a rectangular slab simply supported on all sides. When you use a finite element method and you calculate the isolines of equal bending moments, then the bending moment in the x direction will be varying from a minimum to a maximum. At the corners, you will have a hogging bending moment, which is due to the torsional bending moments. In the middle, the bending moment is maximum. And you have this kind of figure. Now, a type 2 slab is clamped or fixed on one side and simply supported on the 3 other sides. So if you make a cross section here, you will see this is clamped and this is simply supported. The other direction, 2 times simply supported. You look at the isolines for the bending moments, then you clearly see the hogging bending moment here, which is the blue one, the hogging bending moment here on this side, where this side is clamped. So when you encounter this as isolines, then you know that this side and this side and this side is simply supported and this is clamped. Type 3, it means that 2 sides are clamped and the 2 other sides are simply supported. You can see the hogging bending moments on the 2 sides, left and right, which is the blue color, and the sagging bending moment, which is the red color. A slab of type 4, it's 2 sides clamped, but 2 adjacent sides, and 2 other adjacent sides is simply supported. Again, when you look at the isolines, you see the blue one is the hogging bending moment and the red one, the sagging. And you will see this is in the x direction, but in the y direction, it's similar, hogging bending moments and sagging bending moments. The slab of type 5, there are 3 sides clamped and 1 side simply supported. And for the bending moments, you have the same type of illustrations. And then finally, slab type 6, all sides are fixed or are clamped. Then you will see it symmetrically. You have the blue hogging moment, bending moment, the red sagging bending moment. For the supports for a slab, we consider linear supports. For instance, vertical walls can be in concrete or can be in masonry. We can also have local supports, which are columns. And then there is another type of support, which is ground-bearing line supports and global ground-bearing supports. Those two, the ground-bearing line support and the ground-bearing global support, we will not consider in the present videos. There is a general theory, elastic theory of slabs, and one of them is the thin plate theory. It's developed by Kirchhoff-Lagrange. and it results in a fourth order differential equation with the unknown wxy, which is the deflection of the slab depending on the x and y coordinate. There is a material constant d, which is dependent of the coefficient of Poisson, the total depth of the slab, and the modulus of elasticity. This equation has its limitations. It means it's only valid for an homogeneous, isotropic, and elastic material. There are no membrane effects. The slab depth is constant, and the deflection of the slab is smaller than 1/5 of the slab depth. And the minimum dimension is bigger than 5 times the slab depth, and it is only loaded in the two main directions. We take now a very small section of the slab. This is the x direction, the z direction, and the y direction. And on each side of that small element, you can imagine the normal stress in the x direction, the normal stress in the y direction, and then the two shear force stresses tau xa and tau xz, like it is drawn here. These are all the stresses on a very small part of the slab. You can convert those stresses in forces. For instance, the Nx force is a normal force on a part of the slab which is perpendicular to the x-axis. And this force Nx is nothing more, nothing less than the integral of the normal stress in x direction over the depth of the slab. This is an infinitesimal small distance, those two dx, dy. For instance, for the bending moment, mx is the bending moment around the x-axis. It is, of course, sigma x, the stress in x direction multiplied by the z coordinate, and then the integral of minus h over 2 plus h over 2. So all stresses on all sides of this little piece of slab can be reformed, or can be the resulting forces can be calculated. Because we said there are no membrane effects, it means that Nx and Ny must be equal to 0, and the same for the shear force, Vxy and Vyx must be 0, because there are no membrane effects. You can now, on a very small part of the slab, you can make some equilibrium equations, and then you arrive at those three equations. Or you can make it yourself a little bit easier, because we know from beam theory that the shear force, Vx, is in fact the first derivative of the bending moment. This mxy, y and mx, x, it means the first derivative of the bending moment in the x direction and the first derivative in the x direction. This is the first derivative in the y direction. So the derivative of the bending moment is equal to the shear force, and the derivative of the shear force is equal to the load, uniform distributed load. So you can understand where those equations are coming from. Now, this is another way of making the notation. Instead of mx, x, you can make delta mx divided by delta x. It's the same. It's just a way of making the notations. You have the three equations. You can now eliminate Vx and Vy, the shear force, and then you have a second order differential equation in M. You only have three equations, but you have 5 unknowns in total. So you need some additional conditions to put to those equations to be able to solve them. And those conditions are boundary and deflection conditions. Starting from this equation, we can now transform it by replacing the bending moment in the x direction, y direction, and the torsional bending moment by the second derivative of the displacement. If you substitute those values, then you arrive at the equation of Kirchhoff and Lagrange. We have now a fourth order differential equation, and when we solve this equation, it will give us the displacement for the coordinates x and y. From those displacements, we can calculate the strains, the stresses, and the internal forces. Closed mathematical solutions exist for this equation, but only for elliptical shaped slabs. Point of attention is that the support reaction, Qx, it's a force per unit length, is not equal to the shear force. For beams, we all know that the shear force at the support is equal to the support reaction. For slabs, it is not. It's more than the shear force at the support. There is an amount added to it, which is equal to the first derivative of the torsional bending moments. For practical calculations, the theory of elasticity of the thin plates will rarely be applied. So we have to look for approximations. Slab theories are always approximations, and we will, in this video, in the series of the videos for slabs, we will go into that more deeply. The bending moments are in a certain direction within the slab plane, but the reinforcements is always put in a fixed direction. So we have to recalculate all forces in the directions of the reinforcement, or you calculate the reinforcement in the directions of the different forces. We are not going into detail into that, but you should know that the bending moments used for the reinforcement are different from the actual bending moments. We solve this problem in a very easy way by stating that the bending moments for calculating the reinforcements are equal to the calculated bending moments, plus at that location you add up in absolute value or in the same sign the torsional bending moments. This is an upper limit. So at that, then you will make no mistakes or underestimate the reinforcement bending moment.